Hello, my name is John Moyer, and I want to welcome you to the NIH Office of Disease Prevention's Methods Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest in prevention science. Our goal is to engage the prevention research community in thought-provoking discussions to promote the use of the best available methods and to support the development of better methods. Before we begin, I have some housekeeping items. You can submit questions during the webinar via the Q&A pod. You'll need to open the pod by clicking on the Q&A icon. We will open the floor to questions at the end of the presentation. The video recording will be posted on our NIH ODP YouTube channel in a few weeks. At this time, I'd like to introduce Dr. David M. Murray, Associate Director for Prevention and Director of the Office of Disease Prevention.
Thank you, Dr. Moyer. Today's speaker is Dr. Deborah Glick. Dr. Glick is a senior biostatistician at the Life Course Epidemiology of Adiposity and Diabetes Center at the Colorado School of Public Health. She's also a professor of pediatrics at the University of Colorado Denver School of Medicine. She has had a career-long focus on power and sample size for multi-level and longitudinal studies and the analysis of longitudinal epidemiological cohort studies and randomized control clinical trials. Her talk today will describe the impact of ignoring sources of correlation in group or cluster randomized clinical trials based on a review of trials supported by the National Cancer Institute. It's my great pleasure to welcome Dr. Deborah Glick.
Thank you, Dr. Murray. So today's talk is about ignoring sources of correlation in NCI-funded cluster trials increases the chance of decision error. This is joint work with my longtime colleague, Keith Muller, from the Department of Health Outcomes and Biomedical Informatics at the University of Florida College of Medicine. And Dr. Muller will be available during the Q&A section to help me answer questions. Keith and I have no conflicts of interest. This work was supported by an R01 from the National Institute of General Medical Sciences to the University of Colorado Denver. This is the MPIs for that grant were Donna DeBelia, me, and Keith Muller. This is the outline for the talk. We'll go through each section one by one, and you'll see the section headers highlighted before I begin the next section. Introduction. So I give a brief introduction here to what a cluster is. A cluster is a group with membership determined by common exposures, experiences, backgrounds, or interactions among group members or with group leaders. And many authors, for example, Murray, Donner, and Clark, and Campbell, suggest accounting for clustering and for restricted randomization when analyzing data. Restricted randomization refers to trial designs in which randomization is altered to control for baseline imbalances. Many scientists worry that baseline imbalances might lead to bias if they are ignored. So there are three major kinds of restricted randomization. A common approach is to match or stratify clusters into sets based on baseline covariate values. Randomization then takes place within the sets or strata. The most common form of restricted randomization is pair matching. In pair matching, clusters are paired on key covariates, and one cluster in each pair is randomly assigned, often to one of two interventions. The most common form of clinical trials uses only two interventions. Another approach is so-called constrained randomization. Constrained randomization identifies all possible randomization assignments, removes the possible randomization assignments which yield imbalance, leaves only the randomization assignments which control balance of the covariates at baseline, and then the randomization is chosen randomly among the possible randomizations that balance the covariates. Now, most of our talk today is about decision errors, and I'm going to briefly introduce what a decision error is. So a decision error occurs when scientists draw a conclusion from their data that does not match the true state of nature. A type 1 error is a decision error that occurs when the null hypothesis is rejected, even though it is true. By convention, investigators often choose analytic methods which limit the nominal probability, nominal is the claimed probability, of the error to a small value, usually written as alpha, and they often set alpha equals to 0.05. Power is the probability of rejecting the null hypothesis, and a type 2 error occurs when the true state of nature is that there's a real effect. A type 2 error occurs when that real effect is missed. So I'm going to ask a series of rhetorical questions throughout the talk. Here's my first question. What is known about how scientists design and analyze trials with clustering? What I'm going to do here is give a meta review of prior reviews of studies with clustering. So there have been many prior systematic reviews of studies with clusters. So the reason that people have conducted these reviews of studies with clusters is that they have been trying to estimate the rates at which authors perform incorrect sample size selection and conduct incorrect data analyses. Here, I'm going to give a summary of 20 prior systematic reviews of randomized trials with clusters, examining rates of incorrect data and power analyses. So 19 such reviews looked at rates of incorrect data analysis. The median rate of incorrect data analyses was 46%, but the range went from 12 to 100%. The take-home message is that incorrect data analyses were very common among trials with clusters. The story was even worse among when we look at power or sample size analyses. Here, the median among 16 reviews, which reviewed power and sample size rates, was that 70% of studies reviewed showed incorrect power or sample size analyses with a range from 19 to 93%. So we wondered whether NCI-funded trials with clusters have similar issues. And we chose NCI to start with for two reasons. One, NCI was my first funder. My K award was funded by the National Cancer Institute, a grant for which I remain grateful all these many years later, and also because NCI is one of the largest funders of trials across the National Institutes of Health, and in particular, trials with clusters. So we conducted a PRISMA systematic review of NCI-funded studies with clusters. Here, we present the results of our PRISMA systematic review of 96 NCI-funded cluster randomized trials, and we also examine rates and types of incorrect analyses, both data analyses and power analyses. Now, our goal is not to identify wrongdoing. Our goal is to discover how to improve design and analyses of trials with clusters. Now, we carefully thought about the inclusion criteria for our systematic review. We thought that the high proportion of studies with incorrect data or power analyses seen in previous systematic reviews of studies with clustering might have reflected the inclusion criteria that the previous authors had used. We theorized that trials with funding from the National Cancer Institute might include a higher or lower proportion of investigators with expertise in clustering. We also thought that studies with titles or abstracts which included phrases identifying the study as one with clustering might do a better job of accounting for clustering. So here were the inclusion criteria we set up. We included trials with an explicit mention of clusters or groups in the abstract or title. We required that all the trials have at least some funding by the National Cancer Institute, although it did not have to be the major or predominant funding. And we included manuscripts with publication between January 1, 2018 and June 1, 2024. We considered an analysis to be correct if it was clearly described, accounted for the effects of clustering, and accounted for the restricted randomization if present. All others were considered to be incorrect. Two reviewers, so that's Keith E. Muller, my co-author, and DHG, that's me, independently read all manuscripts obtained from our PubMed search. If we had a discrepancy about our belief about whether the power or data analysis was correct or not, we resolved it in an amicable consensus conference. We only looked at analyses of treatment effects on the primary outcome or outcomes and did not review analyses of secondary outcomes. This is the Prisma flow diagram. These slides will be available via a QR code at the end, so I'll go through this rapidly. But essentially, we identified 232 manuscripts, excluded multiple ones for a variety of reasons, and only included 96 manuscripts in the analysis. This still represents one of the larger reviews of studies with clustering. Here are our results. 20.8% of the studies reviewed of the 96 had both data and power analysis correct. Some 5% had incorrect approaches for data analysis, but correct approaches for power analysis. Somewhat more commonly, 11% had correct approaches for data analysis, but had incorrect power. But unfortunately, about 62% had neither data analysis nor power analysis correct in the manuscript. We saw two major sorts of designs of studies with clusters that were included in our systematic review. 31% had only clustering, and 69% had both clustering and restricted randomization. So now let's think only about designs with clustering. So these are designs with clustering, but no restricted randomization. In data analysis, for designs with clustering only, 53% accounted for clustering correctly, but 47% ignored clustering. When we look again at designs with only clustering and no restricted randomization, about 33% accounted for clustering in their power analyses, but almost 67% ignored clustering in their power analyses. Now let's think about the other major kind of designs we saw. These are designs with both clustering and restricted randomization. 23% of such designs correctly accounted for both clustering and restricted randomization in the data analysis. 39% ignored restricted randomization but accounted for clustering correctly, and 38% ignored both clustering and restricted randomization in data analysis. Now we'll think about power analysis. This is for designs with clustering and restricted randomization. About 22%, almost 23%, correctly did the power analysis when they had both clustering and restricted randomization. About 49% correctly accounted for clustering, but ignored restricted randomization in power analysis. And almost 29% ignored both clustering and restricted randomization when they were doing their power analyses. So here's my third question. Does it matter? Why do we care? Now we present exact analytic results for decision errors when clustering is ignored. We first reviewed the literature, the statistical and methodological literature, to see whether other people had considered the size of decision errors when authors ignored clustering or restricted randomization. We found that many authors gave simulation-based estimates. These authors considered only a small subset of the possible kinds of designs. Some authors used approximations to give more general results. Many authors studied decision errors when clustering was ignored, or studied decision errors when restricted randomization was ignored, but we couldn't find many authors who considered decision errors when both clustering and restricted randomization were ignored. Some authors looked at the effect of incorrect analyses on type 1 error, but they did not consider type 2 errors. Recall that type 2 errors wrongly state power and can lead to incorrect sample size choice. So our literature review showed gaps in prior methods' work. We saw three situations in our systematic review in which scientists ignored design features. We saw designs with clustering only when clustering was ignored in the analysis. We saw designs with clustering and pair matching when both were ignored in the analysis. And we saw designs with clustering and pair matching where pair matching was ignored, but clustering was accounted for. For each situation, we computed the exact distribution of the test statistic. We used the exact distribution of the test statistic to compute exact type 1 error probabilities and power when the specified design features were ignored. Now, I want you to remember that we talked earlier about restricted randomization, and we saw three major kinds of restricted randomization. A form of pair matching, where clusters were paired and randomization occurred within the pair. A stratified analysis, in which the clusters were organized into strata by their baseline covariates, and randomization occurred in the strata. And constrained randomization, where only balanced randomization possibilities were allowed. The exact analytic results are only for pair matching and not for stratified matching or for constrained randomization. We assumed that the hypotheses tested were for comparison of means. We assumed that the analyses ignored clustering, pair matching, or both. The derivations assumed reversible mixed linear models with multivariate normally distributed errors, a population covariance following the additive variance component model of Longford, pair matching, balanced sizes of groups or clusters, and tests comparing means. The derivations allow exact results for any combination of cluster correlation, that's the correlation within the cluster, any matching pair correlation, so this is an additional correlation due to matching of the pair, number of clusters, and number of observations within a cluster. The next 3 slides, I'm going to give you graphs of the exact results. Here, we see what happens when there is a cluster randomized design with no restricted randomization and 2 interventions and equal cluster size. Here, we ignore clustering in data analysis. The ICC represents the interclass correlation within the cluster. The nominal type 1 error rate is set to 0.05 and is represented as the golden line horizontal across the screen at 0.05. The results I'm showing you are for 4 clusters, but they are very similar as the cluster size increases. You can see here that as the interclass correlation becomes higher, the type 1 error rate increases, and this is the observed actual type 1 error probability when clustering is ignored. So our goal is to have a type 1 error rate of 0.05, and here we see a strong increase in type 1 error rate for studies with clusters when cluster is ignored. Unfortunately, although some people might think that they will be better off if the cluster size is larger, you can see that the exact results show that the actual type 1 error rate observed if clustering is ignored increases strongly with the cluster size. So neither the number of clusters nor the cluster size will rescue an investigator who ignores clustering in a clinical trial with clustering in data analysis. This shows a study with clustering and pair matching in which pair matching is ignored in data analysis. Here, the nominal type 1 error rate is shown as a horizontal golden line at alpha equals 0.05. Here, the effect is conservative. When pair matching is ignored, you can see that the type 1 error rate becomes smaller, with very many clusters showing the largest decrease in type 1 error rate. Finally, we look at a case when we look at the type 1 error rate when people are ignoring both clustering and pair matching in a study with both clustering and pair matching. Here, the nominal alpha is shown as the golden line at 0.05. You can see that having a large cluster size is no rescue, because with cluster size of 5, we see a small inflation, but when the cluster size is 50, we get a much larger inflation. The type 1 error rate achieves a size of 0.4. That means 4 out of 10 times a type 1 error will occur when both clustering and pair matching are ignored. So in our systematic review of 96 NCI-funded clinical trials with clusters published since 2018, only 21% use correct methods for both power and data analysis. The errors can be substantial. The errors that occur are for the errors when both clustering and, let me start over again. The results I showed you in the graph were for data analysis. Here, on this slide, we're discussing what happens when there are errors in power analysis. The errors can be substantial. The most common error was to account for clustering, but to ignore pair matching. The exact calculations showed that this can cause the number of clusters needed for the study to be up to 25% too large, or as much as 17% too small. Here, I want to take a minute to talk about the human costs of incorrect sample size selection. A sample size that is too large exposes too many people to the possible harms of research, and their exposure to possible harms incurs both human costs and monetary costs without any need. The study doesn't need to be that large. If the study is too small, then participants are exposed to possible harm to research for no additional good. If the study is too small, then the study has a low chance of achieving its scientific goals. We now move to the discussion. The overall message here is in our systematic review of 96 NCI-funded clinical trials of clusters published since 2018, only 21% use correct methods for both power and data analysis. Common data analysis mistakes included ignoring clustering alone, ignoring restricted randomization alone, or ignoring both. Our results are well within the context of other systematic reviews of clinical trials with clusters. Our exact derivations describe the effect of ignoring one of the most important and common kinds of restricted randomization, pair matching, as well as clustering. Our exact derivations demonstrated that ignoring sources of correlated data could lead to actual type 1 error probabilities substantially different from the nominal level, with the amount of error depending on the design, the cluster size, the number of clusters, and the correlations. Our exact results partially mirror those of other authors who used simulations or approximations. We note that these other authors studied the effects of ignoring either clustering or restricted randomization in isolation, but not together. Our results extend the prior literature in several regards. First, our results are exact rather than approximate. Second, they apply to a much larger set of designs than previous publications, including both balanced cluster randomized designs with 2 interventions and designs with randomization of clusters within matched pairs. Lastly, our results cover type 1 error, power, and sample size. Now, several authors have suggested that restricted randomization, but not clustering, may be ignored in sample size computation. Our counterexamples show that ignoring pair matching may lead to sample sizes that are too large or too small, if there's also clustering in the study. Here again, we note that sample sizes that are too large increase costs and possibly endanger study participants for no scientific benefit. Sample sizes that are too small produce trials with a low chance of detecting a real effect. Our work has several strengths. Our systematic review followed PRISMA guidelines for reporting and is among the larger review of trials with clusters. In addition, our work went beyond merely reviewing manuscripts. We derived mathematical results that quantified the possible effects of incorrect analyses on decision errors. The mathematical results extend those of other authors by examining the effects of ignoring both clustering and pair matching. Our work did have some limitations. So first of all, this represents the opinion of two knowledgeable reviewers, that's Keith Muller and Deb Glick, rather than an objective classification scheme. And unlike reviews by Murray et al., we did not include the original design and rationale manuscripts for each clinical trial. Thus, our estimates of the rate of incorrect analyses may have been biased upwards. We also excluded secondary analyses. This exclusion might have inflated or deflated our estimates of the rates of incorrect analyses. Our PubMed search strategy may have incorrectly included non-NCI-funded manuscripts or excluded eligible NCI-funded manuscripts. Finally, by design, our search included only authors who recognized that their trials included clustering. As Bland has pointed out, many authors are completely unaware that their trials involve clustering. We feel that those who fail to recognize clustering are almost certainly unable to account for clustering. Therefore, our estimates of the incorrect data analysis rates and power analysis rates are therefore likely to be conservative. Our analytic work also has limitations. Our analytic results apply only to Gaussian or multivariately normally distributed data and not to binary outcomes. An extension to binary outcomes via exponential family arguments is plausible, but remains to be accomplished. In addition, the derivations as written only concern pair matching of clusters, and they do not involve match sets of more than 2 clusters or constrained randomization. So here are our conclusions. For clinical trials with clusters published by NCI-funded investigators since 2018, the rate of incorrect analyses and the probability of decision errors are both high. To assess the full extent of the problem, we propose to conduct a systematic review of cluster randomized clinical trials for other NIH institutes and centers. We are about 90% done with the results for the National Heart, Lung, and Blood Institute, which is the second largest funder of trials with clusters at the National Institutes of Health. Here's my 4th question. So now what? Well, the high rates of incorrect data analyses persist despite multiple statistical publications, including some of our own, explaining how to analyze studies with clusters. And the high rates of incorrect power and sample size analyses persist despite the availability of free, open source, point-and-click, wizard-style validated software, which computes power and sample size for many of the designs we studied. We have been laboring in this field for decades. Our software, Glimpse, which is hosted at glimpse.samplesizeshop.org. By the way, I will have a QR code coming up so that you don't have to write that down, is free, open source, web-based software for power and sample size for designs with clustering, repeated measures, or both. The software can handle designs with clustering, repeated measures, or both, with or without longitudinal repeated measures. The software has been used for more than 14,000 calculations per year, cited in nearly 500 manuscripts, and used to design more than $200 million in NIH-funded studies. We have also produced an OBSSR-funded short course on power and sample size for multi-level and longitudinal models, which is available on samplesizeshop.org, the same URL which hosts our power and sample size software. But this still raises questions for the community. We have done the best that we can do as tool makers. We have provided methods for people to use when analyzing studies with clusters, and we have provided power and sample size software, which is free, funded by 5 NIH grants, and available to the community. But what is left? What can we do to improve this situation? Who needs to act, and what can they do? We leave community with these questions. We can make tools to help investigators and scientists, but we cannot regulate review by NIH. We cannot regulate review by journal editors. We cannot issue recommendations by societies. We have to leave this to the community. So here, I'm going to pause my discussion. Our slides that I discussed today are available if you use your phone to scan this QR code. The slides that follow this include a recommendation for experts in the field. We had to choose a small number of experts from the hundreds of people who are experts in this field, and we apologize if we did not include you on the list if you are listening in to this seminar now or in the future. So we apologize if we didn't get all of you. We were restricted in space. Also, these slides have made reference to a variety of literature which is important in this field, which was represented by superscripts in the slides. Again, the full slides are available on this QR code, and it has a full references cited section, so you can find all the manuscripts that I referred to. Finally, this QR code will bring you to our website where we have the sample size course, we have the sample size software, and we have a variety of talks and methodological manuscripts freely available to the public. Again, all funded by our previous 5 NIH grants. So at this point, I would like to thank you for listening to me, and I welcome questions and discussion. I'd like to introduce at this point my colleague, Dr. Keith Muller from the University of Florida, who I hope will turn on his video and join me for the question and answer session.
Thank you, Dr. Glick, and welcome, Dr. Muller. Thank you for a very interesting presentation. Got lots of questions. So let's just jump in. You almost answered the first one at the tail end of your presentation. Your report is consistent with earlier reviews going back 30 years, 30, 40 years. Some studies now do a very good job, but as you described, many do not. Given the large number of papers and books that address power and data analytic issues for group or cluster randomized trials, why do we still see so many trials with incorrect methods? And if you can answer that question, I'll buy you a beer.
This is my own opinion. This is not necessarily anybody else's opinion. So including, this may not be the opinion of my co-author, Dr. Mother. But as I mentioned, my K award is from the National Cancer Institute, and I watched the excellent efforts of the National Cancer Institute and others in the great fight to limit tobacco smoking. When I was a child, when you flew on an airplane, people could smoke cigarettes on an airplane, and now they can't do that. And that approach used kind of a public health approach in which everybody in the community was activated. So there were laws made, there was publicity campaigns, and my only thought is that we need action by everybody. Education itself is not sufficient. Tools themselves, such as we have made, such as our power and sample size software, is not sufficient. We need action by everybody, including, I suspect, action by reviewers at NIH, reviewers and funders at NIH, and by journal editors and people who run journals.
Yeah, that sets up my second question. So all the trials that were supported, at least in part, by NCI were reviewed by a study section, either at NCI or at the Center for Scientific Review. So it's sort of the same question. How is it possible that so many trials have incorrect power and sample size analyses and incorrect data analyses after going through this peer review process?
I think, again, this is my opinion and nobody else's. Both Keith and I have served on NIH study sections as permanent standing members. And there are, I think I would have to say that the expertise required to design and analyze trials with clusters is by no means universal, even among members of august standing study sections. My guess is that, and even if there are people on the study section with such expertise, they are only one or two out of a full study section. And the assignment of trials to reviewers is probabilistic. They're unlikely to get a reviewer with expertise in clustering. Even if they do get a reviewer with expertise in clustering, people may not have realized what the effect on decision errors could be for ignoring clustering, restricted randomization, or both. I'm not sure what the answer is here, but I think that the answer, my partial answer is that there has not been enough expertise on study sections in order to accomplish this review and to indicate to both the investigators and to study sections that this problem exists and it can have devastating effects in terms of decision errors.
Yeah, my experience on study section is quite similar to yours, Dr. Glick. I served on about 50 panels before I came to NIH. I can't do it anymore, but back in the day when I was a professor, I could do it and served on about 50. And I was often the only methodologist or the only methodologist familiar with these issues. And one voice in a room of 30 or 40 people, it's often hard to carry the day. Yeah. Let's see. You've talked about NCI trials. As someone at NIH, I'm naturally interested in the issue of, well, what about everybody else? You picked NCI because of your connection to NCI, particularly through your K award. But
Yes.
we have lots of group or cluster randomized trials at NHLBI, at NIDDK, at NIDA, at NIMA, all over the place. So is it likely that we would see the same sorts of issues at the other ICs if you were to pull data on publications based on studies that were supported by those ICs?
I can't answer the question since I don't have the data, but I can say that we are reviewing currently trials with clustering from the second largest funder of trials with clusters at NIH, and we are seeing even worse results for that institute or center. But I don't want to comment on that until the analysis is complete.
Okay, they'll have to wait. If the probability of decision errors is as high as your tables suggest, what is the chance that NCI-funded studies are giving incorrect answers about drugs, interventions, and associations?
This is an interesting question, and it's also almost impossible to figure out because we do not know what the true state of nature is. If we did, then we could figure out that number, but we can't tell you that number. All we can do is produce tools that let you know if we knew what the truth was, what the chance of a decision error was.
I think, though, if we were sharing that beer, you might agree that there's a pretty good chance that we're getting incorrect answers about some of these interventions from some of these studies.
My guess is that we need to do more work to improve correct analyses and correct power analyses in these studies. If we have good analyses and good design approaches for all of these studies, we're much more likely to get good science out of them.
So there are a wide variety of clinical trials that have a wide variety of designs. You have focused on trials that involve clustering. There are a wide variety of designs that involve clustering, and wondering if you looked at the rate of incorrect power or data analysis based on the type of randomized trial that involved clustering. For example, did you compare parallel group or cluster randomized trials to step wedge trials to individually randomized group treatment trials, any of that?
Right, these are great questions, and I didn't have time to talk to have our complete exclusion criteria here. These results presented today exclude step wedge trials, and they exclude individually randomized group treatment trials. So these are for standard or parallel group randomized trials or multi-level trials with clustering. So these results omit the step wedge and individually randomized group treatment trials.
Thank you.
Dr. Muller, I think you're muted, Dr. Muller.
One of the questions that I see asked that has is two that have simple answers. The first is slide 33, a simulation, and the answer is no. Those are exact enumerations from closed-formed analytic results. And the other question is, what is the appropriate method for analyzing restricted randomization and pair matching? For pair matching, the answer is simple. It functionally adds another level of clustering, and therefore one needs to apply multi-level clustering mixed model methods. I hesitate to say I know the answer for restricted randomization because that is a term that describes many possible sampling schemes, and one would have to consider the probabilistic implications of that on a model-by-model basis.
Thank you. You focused on pair matching, and you identified but did not focus on stratification or constrained randomization. Would you expect that the results, if you looked at stratification or if you looked at constrained randomization, would those likely be better, worse, similar to what you found for pair matching?
Well, I'm going to give the answer that I always give when people ask me to speculate on multivariate power results, which is that we don't know. So we can tell you that these results depend on complex quadratic form results, which are almost impossible for us to predict. They have many, many inputs to them. So I think it's worth saying that those are worth studying. Those are either worth studying or it's worth removing the problem. Again, if people did the correct analyses, we know how to quantify the type 1 error and power for correct analyses, and we would encourage those instead.
You're being both
Dr. Muller?
very thoughtful and very correct. Dr. Muller, did you have a comment?
I would add the statement that they are not unanswerable questions. I believe the mathematics is approachable. With support for the time to address the question mathematically, it can be done, and even a simulation study can be useful. I caution that the use of simulations is problematic in that one tends to find answers only where one looks. And so one needs to be careful to examine the range of the parameters of interest to fully worry about what might happen.
I just thought of a way that investigators could use the data that you've presented today, the results that you've presented today. I'm reminded of my former department chair, Russ Lupker, at the University of Minnesota, who is one of the people that taught me how to write grants and was a mentor for many years. And he always liked to put a fancy methodological twist into a grant application. His advice was, geez, that gets the attention of reviewers. It makes you look different from others. It'll give you a boost in the review. And it seems to me that people could point to your work and say so many studies that are supported at NIH are using inappropriate methods. We are using correct methods, if they can actually make that claim, and try to separate themselves a little bit from the crowd. So I just offer that as a comment. How can investigators learn how to do all of this stuff correctly? How to do the correct power analysis? How to do the correct data analysis? I know you have courses, I think, that are maybe available. There may be other resources that you can point to. I'm convinced that people can learn, but how do we help them?
Well, we have tried to help them, and so our website, which has been supported by 5 NIH grants, provides 3 sources of resources in this field. So first, there's a variety of methodological publications that are there for people who want to read methodological publications and tutorials. Second, we have complete a short course that was funded by the Office of Behavioral and Social Science Research, which we taught at 5 different universities and made into a massive online open course. That course survives as online video lectures with exercises on our website available by scanning the QR code. And lastly, we have power and sample size, point and click, free software for studies with clustering with and without longitudinality at multiple levels, an arbitrary number of treatments, variety of things with examples and publications, also available at this QR code. So that is what we have done to try to help solve this problem. It's not enough. We need more.
Thank you. One of our viewers commented, it would be interesting to estimate the impact on power and type 1 error explicitly by getting a sample of studies and estimating the ICC from their data and seeing what the impact of being wrong is in those studies. It would also be good to know in what circumstances ignoring those correlations would be okay. So that was a comment that we got from the audience today. My question is, would you ever advise investigators to ignore correlation due to clustering or restricted randomization? I think I know the answer, but I'll pose the question.
I would like Dr. Muller to comment on this in a calm and rational way.
That's encouragement from my fabulous co-author that I always treasure. We have a paper in review currently, and the title of the paper is Never Ignore Clustering. And I chose that rather forward title because it reflects my philosophy. It does not mean that there are not situations in nature in which ignoring may have been ignored without cost. But it is the case that we can never know when that is. There is a circularity involved, which is if one uses an estimate of an intraclass correlation, that itself is a random variable. It's an estimate. It may or may not be the true value. And so one cannot provide a proof by example. One must examine the mathematics and ask, what if the population correlation is a very small correlation? How much is there an impact? What if it's a big one? That answer depends upon the dimensions of the study, what cluster size there is, and how many clusters. And the answers are often quite surprising. We also, in that paper, Never Ignore Clustering, in one of our papers that are under review, I should say, we have addressed the question of using rules of thumb about when you're safe. And we provide analytic results, which we think are compelling, and we hope you will too when they're published, that one cannot be certain that one is safe. One can only be concerned.
Right. When I've been asked this question, I've generally said the prudent thing to do is to reflect all sources of random variation in the analytic model in the sample size calculation. In other words, all sources of correlation, as you've describing. And if the magnitude of the correlation or the magnitude of the clustering effect is very small, you won't pay much of a price. And if it is, you'll have a properly designed study in terms of sample size and analytic methods. So I think the prudent course is to pay attention to these things. You can never know going into the study what the magnitude is going to be. As you said, you can have estimates, but those estimates all have noise, are never precise. We have a question about implementation research. With the increased emphasis on implementation research where clustering is almost required, how can we increase the knowledge and acceptance of the material that you're talking about in that community? What's a good way to do that?
I don't know. I wish I knew. So I feel like we almost need an implementation science approach to get the answers out to the scientific community. And I would welcome help from the implementation science community to help teach me how to write a grant so I could promulgate our work more broadly.
I want to thank you both for a terrific webinar today. And an interesting Q&A here after your presentation. This material is certainly near and dear to my heart. I've been working in this content for a long time, as you both know. The results that you've presented are very consistent with what we've seen previously. We can have even more faith because of Keith's wonderful work working out the exact calculations, the math. I hope that investigators who've been listening today will take this seriously and look at the various courses and papers and tools that are out there and available to help them use the appropriate methods. I hope our colleagues at NIH who have been listening will look hard at the methods that they use to evaluate clinical trials and try to do a better job in that. It seems to me that if we could intervene at the time that investigators are submitting applications to NIH and identify issues and ask investigators to fix them before funding decisions are made, that would be the way to go. So maybe something we can work on. Again, I want to thank you both, and I will turn this back over to John Moyer.
Thank you, Dr. Murray, and thank you to everyone who participated in today's webinar. We will be posting a recording of today's webinar on the NIH ODP YouTube channel in a few weeks. Thank you, and have a great rest of your day.